Hello guys, my name is Aaron May. I'm helping Miss Knaffer with section 4.3, which is connecting f prime and f double prime with the graph of f. So overall, pretty basic stuff. It's just kind of corresponding, doing derivatives with how they relate to the graph. So I won't be doing too many problems because it's pretty repetitive. So we're going to start out with the simple one, number 7, and the equation is y equals x squared minus x minus 1. Okay, so the first thing you need to do with these problems is you just obviously need to take the derivative. So the derivative of this is 2x minus 1, and then the second derivative of this is just 2. Okay, so part A in number 7 asks, use analytic methods to find the intervals on which the function is, and for A it's increasing, okay? So we know that from the first derivative, right, if we set 2x minus 1 equal to 0, we eventually get 2x equals 1 divided by 2 divided by 2, so x equals 1 half. So 1 half is going to be a critical point. So because 1 half is a critical point, and given this equation, we know that the equation is increasing on 1 half to infinity. All right, so they ask for where it's increasing, so it's 1 half infinity, and this is a bracket. Yeah. Okay, so 1 half is the only critical point. So B asks where it is decreasing. So because it is increasing here, and this is a critical point, we know that it is decreasing on negative infinity 1 over 2. Alright. C asks where is it concave up? Well, we know concave up or concave down due to the second derivative, which is right here. So because this is positive, the whole equation is the whole graph is always concave up. So f is always concave up, never concave down. Okay, so D, this is kind of D. We said it's never concave down right here. And then E asks for the local extreme values. So we established that the critical point is 1 half, right? That's the x value. So to get the y value for the point, we need to plug this x value back into the original equation, not the first derivative equation. We need to do it to the original equation. So 1 half squared minus 1 over 2 minus 1, which is 1 over 4 minus 1 over 2 minus 1, which is 1 over 4 minus 2 over 4 minus 4 over 4. Which eventually equals negative 5 over 4. So that's going to be your y value right here. So, so this is the local extreme value. So we got 1 half from before, negative 5 over 4 from plugging it into the equation. And this is a local extreme value because it goes from negative to positive. Alright, so now we're going to skip around. We're going to go to, so all of the rest of the problems in this section are pretty much the same thing, just taking the derivative and the second derivative equations, then setting them equal to 0, and then finding the extreme values, and then seeing where they increase or decrease. So now we're going to do a problem that's like a little more practical. So in number 37, it asks, a particle is moving along a line with position function s of t. Find the a velocity and b acceleration, and c describe the motion of the particle for t is greater than or equal to 0. So for a, it asks for velocity of the equation s of t equals t squared minus 4t plus 3. Now I change these to x just because it's easier, so we're going to do f of x equals x squared minus 4x plus 3. Alright, so velocity is just the first derivative. So
Okay, you done with your heat test, Daniel? Okay. We'll go over, I'll show you how to do the time test.
the first derivative of this equation is 2x minus 4. So this is the equation for the velocity of the particle, and then to get the acceleration is the second derivative. So second derivative of this is obviously just 2. So this is the equation for acceleration, and this is for velocity, and this is for acceleration. Okay, so we did A, B was acceleration, and then C asks, describe the motion of the particle for t is greater than or equal to 0. So we know that it starts out at 3 because this value, the y-intercept is 3, right? And then it moves negative. So, when t equals 2, right? So when t equals 2, it's the y value is -1 because you can, if you plug 2 in this equation, you get -1, and then past this point, it is positive after 2 comma -1. So that's basically describing how the particle is moving. And then finally, we're going to do a problem on it's number 48, and it gives you a series of it says use behavior to sketch. So sketch a continuous curve y equals f of x with the following properties. Label coordinates where possible. Alright, so I'm just gonna so basically I'm not gonna rewrite all of the properties because you should have them in your book. So basically the graph, you can tell from the x and y values that it's only going to go between the x values and the y values are both going to go between 0 and 8, nothing negative. So we can start our graph just like this, start at 0, 1, 2, 3, 4, 8, Okay, so as you can see on your problem, it gives you 3 x and y coordinates, right? So we have, the first one is 2 comma 1. So we're going to start off labeling 2 comma 1. And then the second one is 4 comma 4. So we're going to label all of these. This is 4 comma, this is 2 comma 1, 4 comma 4, and the last one is 6 comma 7. Okay, so the first property it gives us is that from x is less than 2, the curve is falling and concave up. So we know that it's falling here, but it's still concave up. So this right here is pointing up, okay? Then so between x equals 2 and x equals 4, it is rising and it's still concave up. So rising, and this is still pointed up. This is still concave up. Concave down would look something like this, okay? Then from 4 to 6, it is rising, concave down. So it's going to go to here, and it's going to, this time, the curve is pointed down here. So this is concave down, right here. Up, concave up, concave up. Okay. Then after x equals 6, it is falling, concave down. So it's going to look something like this. This is falling, concave down. Okay, so that's kind of a brief overview of section 4.3, connecting f prime and f double prime with the graph of f. Overall, it's pretty simple. It's just it's really reliant upon, there's nothing really like new in this section, just reliant upon taking the derivative, taking the second derivative, and then setting them equal to 0 and finding all the critical points, and then knowing that if it goes from like decreasing to increasing, that's a local min, and if it goes from increasing to decreasing, that's a local max. And then once you get those points and know where it is, you plug the x value back into the original equation to get the actual coordinate, the actual x and y coordinate. And then So then applying this practically, remember the first derivative is velocity, and the second derivative is acceleration. And then when graphing it, the graphing problems are probably the easiest, especially when they give you the properties, because all, you just first start off by plugging in the coordinates that you know, and then it's pretty simple as far as the direction it gives, like following concave up, concave down, inflection point, rising, concave down, horizontal tangent. So that was brief. So if you have any questions, you can contact myself, Aaron May, or Miss Knaffer. Thank you.